To introduction to mathematical statistics, and then today we will continue with conditional probability. My name is Conditional. Don't forget to subscribe to this channel and try to share with other fellow PhD graduate students and master students. So let's see. So what is a conditional probability? So let's definition. You have let C1, C2 be two events, and the conditional probability of C2 given C1 is defined as probability of C1, so C2 given C1 is equal to the probability of C1 intersection C2 over probability of C1 if P of C1 is greater than 0 and then 0 otherwise. So that forms the basic definitions of conditional probability between two events. So we can verify that one probability of C2 given C1 is always greater than I equals to 0 for any C2 that belongs to our Bohr sigma field, and then for pairwise disjoint, set, so we have Cn belongs to our sigma field, then this called C1 and C2 union C3 union ... given C1 is equal to probability of C2 given C1 plus probability of C3 given C1 plus ... Okay, then that's the probability of C1 given C1 is equal to 1. So you can verify all these basic theorem on conditional probability. So you also have what we call multiplication rule. So probability of C2 given C1 is equal to probability of C1 intersection C2 over probability of C1. So if it was multiply, this implies the probability of C1 intersection C2 is equal to probability of C2 given C1 times probability of C1. We have verified that our probability of C1 intersection C2 can also equal to probability of C1 given C2 times probability of C2. So that is what we call our multiplication rule. So let's check some examples. Now look at this example. So a hand of 5 cards is to be dealt at random without replacement from an ordinary deck of 52 playing cards. So we have to find the conditional probability of an all-spade hand, given that there are at least 4 spades in the hand. So probability of C1, given that we have C2, and that's equals to probability of C1 intersection C2 over probability of C2. So note that C1 intersection C2 is equals to C1. Why? Because C1 is it contains spade of which it always contains 5 spades. Because find the conditional probability of an odd spade hand, and we only have 5 fingers of a poker's hand. So why C2 contain at least 4? That means that it contains 4, 5, 6, 7 down to 13, because we have 13 spades. So 5 intersection this will actually give us 5. So that's why we have that. So then we need to find the probability of C1, which is the conditional probability of odd spade hand. So we know we have 13 spade. Out of 13 spade, we pick only 5 out of it. Then the total outcome is 52 over 5. So our conditional probability of C2 is that at least 4 spade in the hand. So at least 4 spade in the hand. That means that out of 13 spade, we picked 4. So if we pick 13, 4, and then don't forget we still have to, our hand have to be 5. That means that we picked, if we subtract 13 from 52 cards, that means that we pick 39. We pick the remaining one from the main 39, or we pick the whole 5 from the 13 spade over the favorable outcome, which is 52.5. So let me explain this further. The cases we have here is that we have probability of at least 4 spade at hand. That is case 1, at least 4 means that we have 4. Then 1 another kinds. Okay, and let me say 1 another suit or 1 another kind. So okay, we pick the old 5 spades. So that's why we have these two cases. So therefore the probability of C1 given C2 is equals to 13 combination 5 divided by 52 combination 5, everything over 13 combination 4, 39 combination 1 plus 13 combination 5, everything also over 5th condition 52 degree 5. So this cancel this. So we are left with 13 combination 5 over 13 combination 4, 39 combination 1 plus 13 combination 5. So if you solve this carefully, then you have something 0.0441 as your result. Okay, so let's check another example. So for another example, let's see what we have. So a boat contains 8 ships. 3 of the ships are red and the remaining 5 are blue. So let's illustrate that. We have 8 ships. We have 3 of the ships are red and then 5 are blue. We have 5 blue. We have 3 red. So everything make up 8 ships. So 2 ships are to be drawn successfully at random and without replacements. Wants to compute the probability that the first draw results in a red ship. So if the first draw is red ship, probability of C1, which is red ship, we have 3 red ship and we have total number of 8 ships. That means we have 3/8. And that the second draw results in a blue ship. Don't forget, we are drawn successfully without replacement. So the second draw, probability of C2, given that we have already drawn C1. So the remaining ships left here will be 7. Then out of those 7, we want to draw a blue. We see have 5 blue, but we now have 7 ships left, and that gives us the desired result. So you can also compute it by going through the definition given above. So another question, another example. So let's check another example. Okay, apart from an ordinary deck of playing cards, cards are to be drawn successfully at random and without replacement. Then we have to find the probability that the third spade appears on the 6th draw. So let A1, or let just A be the event, or be such that we have to be drawn at random without find the probability that the third spades appear. That means that the first 2 spades appear in the first 5th draw. That means that we have 2 spades and then 3 other suits, or we can just call kinds. So we have this, and then let's be third spade appears and the 6th draw. That means the first draw we have 2 spades, so probability of A. So we have 2 spades, we have 13 spades, we pick 2, then we have 39 times left, then we pick 3 over 52 over 5. Then the probability that the 5th draw not occur. So if we solve this carefully, then we have 0.2743. That is probability of A, that's the first to occur. So probability of B given A. So don't forget, we have already picked 5 cards. The cards that remain out of 5 is 47. Now we want to pick another spade. Don't forget that we have already picked 2 spades. So the spade that will be left over is 11. And if we solve this, we have 0.2340, and that gives us our desired results. Okay. So having this result, then we can now find the probability that A intersection B, and the probability that first the cards to occur in the to spade in the first draw, and then the event of a spade on the 6th draw. So that is going to give us probability of B given A times probability of A, and that is equals to 0.23743. So 2743 times 0.234 is 0, and that gives 0.0642. Okay, and that is we actually make use of multiplication rule for that. So we can also define multiplication rule for 3 sets. Multiplication rule so probability of, for example, C1 intersection C2 intersection C3, that is equals to probability of C1 intersection probability of C2 probability of C3, given that probability of C1 intersection C2, and we can simplify this to probability of C1 times probability of C2 given C1 times probability of C1 intersection C2 given probability of C3 rather given C1 intersection C2, and then we can also continue like that. So for n case, after C1 intersection C2 intersection dot dot dot, and the probability of C1 times probability of C2 given C1 dot 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 probability of CK given C1 intersection dot 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 intersection CK minus 1. Alright, so let's check this example. So let's check this. We have 4 cards are to be dealt successfully at random without replacement from an ordinary deck of playing card. But to find the probability of receiving a spade, a heart, a diamond, and a club in that order. So let's just denote as probability of our event a spade, a heart, a diamond, and a club. So in the first, if we pick spade first, then we have 13 spade, so we pick 52 times the second one heart, we have 13 heart, but we have 51 card left. Diamond, we still have 13 diamond intact, but we have 50 card left. And for a club, we have 13 club left, but we have 49 cards left. So if you take the multiplication of all this, then you're able to get a reasonable result. Let me quickly confirm the result of this. So you have 0.0044. So you can confirm that. So now we want to define what the law of total of probability is. The law of total probability and the Bayes theorem or Bayes formula. So total probability let's see one then let's see any partition of our sample space. Then for any event given C, we have probability of C is equal to probability of C1 given C2. So we have probability of C1 times probability of C given C1 plus plus probability of Cn times probability of C given Cn. So with that, you can now define Bayes' formula. Bayesian formula, probability of Cj given C is equal to probability of Cj intersection C, or probability of C, and this is equal to probability of Cj times probability of C given Cj over probability of C1 times probability of C given C1 plus probability of Cn probability of Cn so probability of Cn times probability of C given Cn. So let's check the implication or an example using this formula. Let's check this example. So it is known that bowl C1 contains 3 red and 7 blue chips. So let's go this bowl 1, bowl 1, this is bowl 1 and it contains 3 red and 7 blue. So it's 7 blue. And then bowl 2 contains this bowl 2 contains 2 red, 8 red rather, and 2 blue. So all chips are identical in size and shape. So a die is cast and bowl C1 is selected. So we have a die and bowl 1 is selected if 5 or 6 spots show up. So then that's a die is from 1 to 6. So if you have 5, different color. So if you have 5 or 6, then we pick bowl 1. Then otherwise bowl 2, that means if you have 1, 2, 3, and then 4, we pick bowl 2. So the selected bowl is handed to another person and one chip is taken at random. Let C be the event that this chip is red. So red chip is picking. So we pick a chip red. So we don't know where it's coming from. So we have to find the conditional probability of both C1. Probability of both C1 given that a red chip is drawn. So in that we have to calculate probability of C1 given that a red chip is drawn, that is C. That's probability of red. So using our formula from here, So probability of Cj given C is equals to probability of C1 intersection C over probability of C, and then by what you divide is equals to probability of C1 times probability of C given C1 over probability of C1 given probability of C given C1 and plus probability of C2 times probability of C given C2. Okay, so our probability of C1 and then probability of C2 is now equals to, going using this formula, probability of we picking C1 is by way throwing these two dice, and that is equals to 2 over 6 times probability of C from both C1. So we have 3 red ball out of 10 over, then we also have probability of C1. Probability that we pick C1 is 2 over 10 times probability of we pick if we choose C1 we pick red ball from there, that is also 3 over 10 plus probability of picking C2, that is 4 over 10, and probability that we pick a red ball here is 8 over 10. So if we solve all this, we have 3 over 19. Okay, so the probability, so remark for this from this question is that note the probability of C1, which is equals to 2 over 6, and probability of C2, which is equals to 4 over 6, are called real probabilities. Okay, and the one we get later on, probability of C1 given C, which is equals to 3 over 19, and then you can also show probability of C2 given C, that's equal to 16 over 19, are called posterior probabilities. Okay, so I have another question here, and an example. So 3 plants, C1 and C1, C2, C3 produce respectively 10, 50, 40% of a complex output. Although plant C1 is a small plant, its manager believes in high quality and only 1% of its products are defective, while the other two, C2, C3, are worse and produce items that are 3 and 4% defective respectively. So all products are sent to a central warehouse and one item is selected at random and observed to be defective. Then we call that event C. What is the probability that it comes from plant C? So let's check the solution. of this. So we have plant C1, plant C2, plant C3. So our posterior, superior, and inferior probability for C1 we have 0.1. We have 10% product, so we have 0.1. Then 50% of outcome for C2 we have 0.5. Then for 40% for C3 we have 0.4. Right? So, and other 1% of it, this is superior probability. So percent of defective from C1 is 1%, that is 0.01. From C2 we have 3%, that is 0.03. And from C3 we have 0%, we have 0.04. So the probability of C1 given C is probability of C1 intersection C over probability of C which is defective, and that is equal to probability of C being defective times probability of C1 coming from C, and we can just write it as probability of C1 defective C times probability of C1, probability of C given C1 over probability of C times probability of C given C1 plus probability of C2 times probability of C given C2. So then for the last one, reduce the size. Then plus probability of C3 times probability of C given C3. So probability of C, so we have this point, we have 0.1 times 0.01 over what? Over 0.7 0.1 times 0.01 plus 0.5 times 0.03 plus 0.4 times 0.04, and if you get the calculation carefully you have 1 over 32. Okay, so in our next video we try to check independence, then we check some exercises under conditional probability and independence. Hope to see you in the next video. Thank you.